So it's a pleasure to have Alvaro Lozano-Robledo from the University of Connecticut give us a talk today, which is titled Towards the Classification of Adelic Galois Representation Attached to Elliptic Curves over Q.
Well, thank you, Philip, and thank you, everyone, for coming and for the invitation to give a talk here. It's a pity that I can't be in Zagreb again. I was there in 2018 for a conference that Philip and others put together. This is the picture of the conference. Where am I? I'm here somewhere. I'm like right there. And it was amazing. I had such a great time that I really wish I could have been again. By the way, I am wearing a University of Zagreb T-shirt just for the occasion. So anyway, so what I would like to talk about is about adelic representations attached to elliptic curves. We're going to get there. I'm going to define these things and explain why they're important first. The title is to indicate towards, like, we're really far away from this classification, but this is my goal, and we're extremely far away from the goal. But we are. I just want to talk about a number of results that that have been appearing in recent years, and if you put them all together, they look nicer when you know what this is about. It's about classifying these adelic representations and what are the possible images of such representations. So let me start so with another picture. So here is, so we are going to start with an elliptic curve, and we are going to attach this object, representation of the absolute Galois group of Q that maps to GL2 of Z hat. This is the profinite completion completion of the integers. And what that Galois representation encodes is all the information we have about how the Galois group, the absolute Galois group, acts on points. So in the picture, there is an elliptic curve, P is a point of order 5, and the lines in red are meant to indicate an action of Galois. So for example, automorphisms of Galois can send P to 2P, and that same automorphism determines where all the other points of order 5 go. So in that action, if P goes to 2P, then 2P goes to 4P, 4P goes to 3P, and then 3P goes back to P. And that action gives you pieces of the adelic Galois representation, and every such action goes into it. And if you know all the action of Galois adelically, then you know all these such actions, and then you can construct things and know things about the elliptic curve. So let me tell you what kind of things you can know about the elliptic curve if you knew these adelic representations. So first of all, if you have an elliptic curve, we have the Mordell-Weil theorem that tells you that the points on the elliptic curve over Q, which is ultimately what we're interested in, is understanding all the points and how to compute such points on elliptic curves. So the points over Q is a finitely generated abelian group. That's Mordell-Weil theorem. In this setting, over Q is just Mordell's theorem, really. But the point is that if you extend that to Q bar, then the points over Q bar, that is not a finitely generated group that has, it's still an abelian group, but it has infinite rank. However, the torsion subgroup is well understood. We know the structure of that torsion, so you just have to adjoin all the n torsion points. They're all points of finite order, and the points of finite order, the points of order dividing n, what we call the n torsion subgroup, we know it's isomorphic to 2 copies of Z mod n. Here is 2 copies because we're working in characteristic 0. If you change this and talked about elliptic curves over fields of other characteristic, then these might change a little bit. But the key here is that there is an action of Galois. So the Galois group, because addition is a morphism that is defined over Q, so it's just polynomials defined over Q, the points of order n are permuted by the action of Galois. So if you have an automorphism of the Galois group and a point defined over Q bar that is of order n, when you act with Galois, that action commutes with addition, and it gives you another point of order dividing n. And that induces a representation of the absolute Galois group of Q. So, so again, if you have points over Q bar, there is an action of Galois, and then you can ask, what are the fixed points of such action? So the fixed points are, if you have an elliptic curve over Q and you have fixed points by Galois, the points that are fixed by every element of the Galois group are those points that are defined over Q. That is the content of Mazur's theorem that proved the Levi-Ogg conjecture. What are the possible torsion subgroups that appear over Q? And those are here. There is points of order n up to 10 or 12. There are no points of order 11. And then the torsion subgroups can be bicyclic of order or structured Zimod 2 cross Zimod 2m for m 1, 2, 3, 4. Then the next thing you can ask is to relax that. Instead of looking at fixed points, you can look for subgroups that are fixed by Galois, that are Galois invariant. So not just points that are fixed point-wise, but an entire group that is fixed. It might be sent, one point may be sent to a multiple of each other, like in the very first picture that I had, but those are fixed by Galois, right? So in here, the point P was not fixed by Galois, but the orbit of P, P, 2P, 3P, 4P, here, 5P is 0, 5P is O, the point at infinity, then that orbit is Galois invariant, and that's what I mean. What are the possibilities for such Galois invariant subgroups? That has a long history, and a lot of people contributed to the full classification of this. Mazur was the one that really completed that classification, or not completed actually. The more difficult step of the classification was proved by Mazur, which was what are orders that are prime can occur, and he proved that after 163 there are no more isogeny, there are no more cyclic groups that are Galois invariant after 163. But in any case, the complete classification is known, and if you have a point that is a finite order and the orbit is Galois invariant, then the number of points or the order of that point can be 1 through 10, 12, 13, 16, 18, or 25. And for each one of those orders, there are infinitely many J invariants for each one of those possibilities, just like there are infinitely many J invariants where that happens for each one of the torsion subgroups that appear in Mazur's classification. But there are other points of orders 11, 14, 15, 17, 19, 21, 27, 37, 43, 66, 7, and 163, where only finitely many J invariants have a point that is generator of a cyclic Galois invariant group. For example, for 27 in particular, if you have a point of order 27 such that the orbit is Galois invariant, then you know the J invariant. The J invariant is this number, minus 2 to the 15 times 3 times 5 cubed. And that's because there is that elliptic curve has complex multiplication. But in any case, that's the only one where that happens. Okay, so let me combine the previous two results. By the way, points that generate a cyclic subgroup that is Galois invariant, those correspond to isogenies. Basically, they correspond to isogenies via if you take that and then do form the map that goes from E to E modulo P, then you get an isogeny that is defined over Q because the kernel is Galois invariant, and it gives you an isogeny defined over Q. So isogeny defined over Q with cyclic kernel and subgroups that are Galois invariant of finite order, those are in correspondence. So here's something that one of my students, Garen Chiloyan, that was a problem that I proposed for his thesis, was the following. So if you have an isogeny defined over Q, then now you have two possible torsion subgroups, the torsion subgroup of E, the torsion subgroup of E prime. So the question was, what are the possible combinations of the pair of torsion subgroups for E and E prime? More generally, the question is, if you have an elliptic curve E1, then you can look at the entire isogeny graph or the isogeny class, look at all the curves that are isogenous to that elliptic curve. So for example, in this case, there is an isogeny class with 4 elements. And now we want to know what are the possible torsion subgroups in each corner of an isogeny class, of a fixed isogeny class. At the same time, what torsion subgroups can occur. And so more explicitly, here's an example. So if you take E to be the curve in LMFDB label, this is the LMFDB label 17A2, which is given by this Weierstrass equation. That elliptic curve has this isogeny class. So this is E1. And then there are another 3 curves that are 2 isogenous to it. And I'm not going to give you the equation of those. And in that case, what happens is that the torsion subgroups that occur are Z mod 2 cross Z mod 2, and then 2 copies of Z mod 4, and 1 copy of Z mod 2. Okay, so we call this an isogeny torsion graph. And it's a graph that keeps track of what curves are isogenous to your given curve. And it also keeps track of the isogeny degree. So that is part of the information that is recorded by the graph. And in each vertex, we record the torsion subgroup that is in the vertex. So it's not like I wrote before, it's not just a vector of torsion subgroups. It actually matters that at some point the graphs are going to be big enough that it matters where these torsion subgroups are located, that a permutation of those actually would give you 2 isogeny graphs, isogeny torsion graphs that are not isomorphic. I'm not going to get into all the details of that, but the theorem is that there are precisely 52 isomorphism types of isogeny torsion graphs attached to isogeny classes over Q. Okay, and I'm not going to give you an entire classification, but I do wanted to give you some examples where, first of all, what kind of isogeny graphs are there? This, by the way, the classification of isogeny graphs, this was known, but we couldn't actually find a proof of this classification in the literature, so we actually wrote a complete one in the paper. But in any case, the possible isogeny graphs over Q, okay, this is what isogeny graphs appear over Q are these. There are linear graphs with 1 vertex, 2 vertices, and an isogeny of degree P, 3 vertices, or 4 vertices, and you see that here now I wrote 3, 3, 3. That's because if there are 4 vertices, then this elliptic curve has an isogeny of degree P cubed, and that it can only happen if P is 3 and the isogeny has degree 27. And remember that I told you from the classification of isogenies that that elliptic curve is actually, there's only 1 J invariant where that happens. Then there are what we call TK graphs, T for 2 torsion. These elliptic curves only have isogenies of order a power of 2. There is like what we call a T4 graph, a T6 graph, and a T8 graph. Then there are rectangular graphs where there's two different primes, isogenies of degree P and the isogenies of degree Q. It can be a square or an actual rectangle. And then there's what we call the special graphs, which are graphs where there is a T4 structure happening for the two primary component, and then there is an additional 3 isogeny that gives you this sort of like shift, and then you can see there is a second T4 structure in the graph. Okay, so those are the possible isogeny graphs, and then I can give you, for example, what happens with the TK graphs. So in the TK graphs, what Garen's shown, I contributed actually in the classification of the S graphs. So what Garen shows is that the possible isomorphism types of the isogeny torsion graphs are given here in this column. So you see that, for example, in the T4 graphs, we've seen an example of this graph, right? Oh, by the way, this means this notation here. That would mean Z mod 2 cross Z mod 2, while this means Z mod 4, right? So this says that, yes, there can be in the corners of the graph, there can be a Z mod 4, a Z mod 4, and a Z mod 2, but actually you cannot have Z mod 4, Z mod 4, and Z mod 4 on all 3 corners. Okay, so that's something that, that's part of the classification of things that you have to rule out, that cannot happen. Okay.
Ok, ajde bok. Bok.
I do not speak Croatian, so. Was there any question?
I think this was not towards you. I think he was answering the phone.
Okay.
Mute himself.
Okay, no problem. Okay, very good. So this is the classification, just an example of what happens with the T graphs. And we have in the paper, you can find tables for all the other types of isogeny graphs. Okay, so but what do all these results have in common? Mazur's classification of torsion graphs of torsion subgroups over Q, the classification of what isogeny, cyclic isogenies happen over Q, isogeny torsion graphs. And the key is that all this information is actually encoded in the adelic Galois representations. And each one of these information is telling you some bits, some pieces of things that happen in the adelic Galois representation, but not the entire Galois representation, just some sort of like bits of information that happen there. So what happened is that, so we have the N torsion subgroup and the Galois group acts on it, and that induces a representation of the Galois group it maps to the automorphisms of En, and that upon choice of a basis of En, since it's Z mod N cross Z mod N, the automorphisms, that is isomorphic to GL2 of Z mod NZ. And the image here tells you the information about the questions we've had before. What we're going to do later on is put all the information together into what we call the Tate module of the elliptic curve. I'm going to do an inverse limit of all N torsion subgroups, and that's going to give me something that is isomorphic to 2 copies of Z hat, the inverse limit of Z mod N, and that is going to induce a representation from GQ to GL2 of Z hat, which actually encodes all the possible row En, all of them in one package. Okay, so this is what we're going to do later, but for now, let's just look at the information modulo N already tells you about all these examples that we've given you. So for example, if you have, if you're thinking about Mazur's theorem, an elliptic curve that has a torsion subgroup, if you're looking for elliptic curves with torsion subgroup Z mod 8 cross Z mod 2, what that means is that there is a basis of the 8 torsion such that there's a point of order 8 defined over Q, and a point of Q of order 8, such that 4 times Q is rational. It's a point of order 2 that is rational, and that is encoded in a Galois representation by telling you that what happens in that Galois representation, modulo 8, it tells you that the image of Galois is, it maps into a subgroup of this form. The first, so this is already in the basis. With respect to the basis PQ, P has to be fixed, so it's always sent to itself, and Q is sent to something such that when you reduce modulo 2, you actually have that all the 2 torsion is defined over Q. Okay, so in any case, that is the image that it has to be inside GL2. It cannot be all of GL2 Z mod 8. It has a particular image, and that image tells you about the torsion subgroup that the elliptic curve has. What about isogenous over Q? Same deal, that if you have, for example, an elliptic curve with a point of order P that the subgroup of order 163 is Galois invariant, then you can pick a basis with P as the first coordinate vector. And what this tells you is that the Galois representation modulo 163 is of this shape now. It's a Borel subgroup in GL2 of the Z mod 163. And vice versa. If you know that your Galois representation looks like this, then your elliptic curve has an isogeny of degree 163. What about isogeny torsion graphs? Same thing. It turns out that if you have an elliptic curve E with a T4 isogeny torsion graph of this shape, like we saw in the example, and E, your elliptic curve is here right in the middle, it turns out that you can prove that this is equivalent to saying that the mod 4 representation now, it actually lands in this subgroup of GL2 Z mod 4. So it's also encoded, even though this is information about the entire isogeny class, is actually encoded in the Galois representation of one of them, and I believe in the Galois representation of all of them, but it's there in the Galois representations. By the way, I'll mention this later also, but there are infinitely many elliptic curves where the image maps into this group. There's infinitely many non-isomorphic over Q elliptic curves, and that follows from some other result about adelic representations. Okay, so you see that many of these things we are interested in, very concrete things about elliptic curves, that are actually encoded in the adelic Galois representation. So again, now we can put all the information modulo n together via what we call the Tate module, and this is the adelic Tate module of an elliptic curve. You can do this also for p power torsion, and then you get the p-adic Tate module. If you put all the n torsion together, and then you get the adelic Tate module. The Galois action acts on the Tate module, and it induces, induces a representation of the absolute Galois group that maps into GL2 of Z hat once you've picked a basis. So the question which would answer all of the questions about, before, and many other questions about elliptic curves, is what kind of images, what are all the possible images that this adelic Galois representation can have in GL2 of Z hat. We're far from that, but we have quite a bit of understanding now of some important bits and pieces of this. So here's some important theorems. First of all, Serre proved that if the elliptic curve over Q, actually he proves over number fields, but over Q, if there is no CM, okay, if there is no CM, then the image of rho is open for finite index in GL2 Z hat. So this tells you that the image is always very large. It's a very large subgroup of GL2 Z hat. GL2 Z hat is enormous. So the fact that the image is open in there means there's a giant image inside. Another question is, what is the index? And then once you know the index, what subgroup are we talking about? Moreover, in the same paper, actually, well, that paper is amazing, but it's there. I keep going back to it because there's so much stuff in it. Sarah shows that the index is always at least 2 over Q. It cannot be index 1. And in fact, if you look into it, the index is even, is always even. So it's divisible by 2. In the same paper, Serre formulates what's known as Serre's question or Serre's conjecture sometimes. Serre did not and does not agree to call it a conjecture, so we'll keep calling it a question for the time being, is the following. So if there is no CM, again, in the non-CM case, you can reduce, for every prime P, you can reduce the representation modulo P, and then you get a representation that goes, so rho mod P, we call it rho EP, goes into GL2 of Z mod P, so of FP. And then the question is it always surjective for all P bigger than 37? We don't know the answer to that. We have also there's some progress in there, but not complete. And Zewina proved that if you assume Serre's question, then the following is true. So it's a conjecture. I formulated here as a conjecture, but it is a theorem if Serre's question is true, and is the following. Again, if there is no CM, then except for a finite number of exceptions, so except for a finite set of J invariants, then the image has index in GL2. It had one of these numbers. It's a large collection of numbers, but there is a collection of indices that are possibilities. Okay, so we have a list of candidates to look through for these indices. Okay. And the paper is also very rich, and it gives you sort of an idea of like where these indices can come from, and what kind of images would result in these kind of indices. So it's actually quite sort of a roadmap to what adelic representations we can expect in general. Again, there is some finite set of exceptions that that are a little bit more difficult to identify, but I think those could also be treatable. Okay, so there was a lot of no CM, no CM, no CM in the previous slide. So let me just tell you what happens in the CM case. The complex multiplication case is better understood. So if you have an elliptic curve with CM, then what happens is that the J invariants themselves have CM. So if you start with a CM J invariant, and then you go and define an elliptic curve over Q adjoint that J invariant. So this is an elliptic curve now with complex multiplication by an order OKF. Then what I showed is the following. I'm not going to go through the entire slide, but I just wanted to read it all out in, precisely. And the point is that there is a subgroup of GL2 Z mod N, which we call a Cartan subgroup. And these Cartan subgroups, if you do it modulo P, if N is a prime, then these are Cartan subgroups that you probably know and love. For a generic N, these are a little bit more complicated. But in any case, there is what we call the Cartan subgroup, what we call the normalizer of the Cartan subgroup. This is actually a misnomer, because for a generic N, this is actually not the normalizer, but let's call it the normalizer. And then you can do an inverse limit of such groups, and that gives you an adelic subgroup. Okay, so now this would be inside GL2 of Z hat. And what the theorem tells you is that the image is always contained in this normalizer, and then the index of this adelic image divides the order of the group of units of your order that you have CM by. Those orders have very few units. So if J is 0 or 1728, that those units may be 4 or 6. Otherwise, if J is not 0 or 1728, actually the order of the units is just, the units are just plus or minus 1, so the order divides 2. So in general, you have that the image is sort of determined, and in fact, in my paper, I did exactly determine what is the actual image, what subgroup of order 2 is in there, and so on. So again, so the CM case is actually understood what the adelic image is, but notice that this is a much smaller image than all of GL2Z hat. This is not open in GL2Z hat. For the reason that, for example, if you go, there's just a quadratic extension that after a quadratic extension, the image is abelian. The Cartan subgroup here is an abelian subgroup of GL2Z hat. So this is just essentially some sort of like dihedral group in GL2Z hat, which is far from the truth of all of GL2Z hat. All right, so, but the CM case is treatable and we know what happens. So you can forget about the CM case if you want. All right, so now the adelic representation is formed by pieces, which is p-adically. You want to know what happens also with the p-adic Tate module. And recently, there was this huge theorem by Rouse and Zagreb where they completed a classification, again, in the non-CM case, but I've treated myself the CM case separately, that if you have an elliptic curve over Q, then the image of the two-adic Galois representation is one of 1,208 possibilities up to conjugation. And they have a website with a complete like map of every representation that happens, which is searchable, and you can identify all the possibilities. It's great. And the index of the image two-adically, this index divides the index adelically. This index divides 64 or 96, and the two-adic image is defined modulo 32. That means that if you know what the image is modulo 32, then two-adically is the full inverse image of that. By the way, I don't know if I can jump to a page here. Let's see. Rouse and Zurich Brown were at the conference in Zagreb. Where are they? Here is Jeremy, and here is David Zurich Brown. All right, very good. Oh, Sutherland also appeared. Maybe his name didn't appear here, but Sutherland and Zewina also classified, also depending on Serre's conjecture, also classified the possibilities for the mod P image of a Galois representation. While we're here, Harris will make an appearance in a moment, so we'll mention. And I don't think Jackson Morrow was at the conference, who will also make an appearance soon. Okay, anyway, let's go to where we were, maybe here. Okay, yeah, so so the work of Rouse and Zurich Brown tells us what are the possibilities two-adically, and they're working on, for example, a classification of the three-adic case, which would be very useful. But then what you have to do is, once you know p-adic by p-adic Galois representations, that's not enough, because there are interactions between towers that you have to worry about for the adelic representation. So let me show you what are the problems that happen. So what is the largest possible adelic image? The largest possible adelic image is called a Serre curve. So we know by Serre that the image is of index at least 2. So the smallest it could be is 2, and 2 happens. And those are called Serre curves. Okay, so Kojukaru, Grant, and Jones prove that almost all curves are Serre curves, in the sense that if you have an infinite family, a parametric family of curves, then the set of exceptions is thin in the sense of Serre and Hilbert irreducibility. And but the problem with the Hilbert irreducibility is that it doesn't give you any actual examples of things that are Serre. This is just telling you that almost all are in some sort of density sense. Harris, that I just mentioned, so Harris Daniels, who was my student at UConn, he was the first one to write an explicit family of Serre curves. So he has a very nice paper with a very explicit family of Serre curves. Right, so those exist. And then, so why is the index even? Why is the index always even? So the reason is the following, that if you have an elliptic curve over Q, you look at the discriminant, and if the discriminant is a square, then what happens is that already the mod 2 representation is already too small. It's either trivial, in which case all the 2 torsion is defined over Q. So this would say that the entire 2 torsion is rational, or the Galois group is Z mod 3, it's abelian. That is far from being, well, not too far, but far from being all of S3, which would be the entire GL2 of Z mod 2. So in both cases, the index of the mod 2 representation is already divisible by 2, and that gives you that the two-adic image already is even, and then the adelic image will have index dividing index divisible by 2. Now, the other case, which is actually, I think, more interesting, is what happens if the discriminant is not a square. If it is not a square, then this is the first example of what we call a Galois entanglement. So what happens is that the discriminant, the square root of the discriminant, is actually contained in the 2 tower, is contained in the 2 torsion. But if this is non-trivial, this itself is an abelian extension of Q, and therefore by Kronecker-Weber is contained in some cyclotomic extension. But by the existence of the Weil pairing, so this is a consequence of the existence of the Weil pairing, the n torsion of Q bar, so the nth roots of unity are inside the n division field. And those have no business being here. So in here, there is no business of being an intersection of the 2 division fields. And the fact that this is also contained in here makes that these are not as disjoint as they should be for the image to be of index 1 adelically. Okay, so there is what we call a Galois entanglement between 2 fields that they should be separate, and that causes the Galois group to sort of like just crush by a factor of 2. So here's a concrete example. If you have the elliptic curve y squared plus y equals x cubed plus x squared, the discriminant is minus 43. So you have that minus, the square root of minus 43 is in the 2 tower, but this one is the quadratic field inside the 43rd cyclotomic extension of Q, and that is inside the 43rd division field. Okay. And that causes that, well, it turns out that the two-adic image by Rouse and Zurich Brown, that is surjective. The 43-adic image is surjective, it turns out. However, the adelic image is not surjective because modulo 86, when you put all these both, when you put these 2 division fields together in the 86 division field, they have an intersection that shouldn't be there, and then cuts out the Galois group by a factor of 2. and that already has, it is not surjective there, and the image has an index 2, and that causes the image adelically to be divisible by 2. And in this case, this was actually an example proved by Sayre that the image is exactly of index exactly 2. Now, be very pay a lot of attention to the equation of the elliptic curve, because in the next example, I'm just changing the sign from plus to minus, and things change quite dramatically. So now this elliptic curve, which is the one that appeared in the title slide, the discriminant is -11. So the same thing happens, that there is an interaction, a Galois entanglement now of the 11th division field and the 2 division field. They're entangled. The 2 adic and the 11 adic are surjective, but not the 22. The modulo 22 is not surjective. That's where the interaction happens. But in addition, there is another problem for the adelic image to be large, and is that there is a point of order 5. So by what we saw by Mazur's theorem, well, the definition by what that means about the 5 adic image or mod 5 image, it tells you that the image is contained in a subgroup of this form. It actually, the image is surjective to this subgroup. The index is 24 here. So that gives you that already mod 5, the index is 24, plus an index 2 of the mod 22 image. Now the index adelically is at least 48. Okay, and I haven't checked this, but I believe the index is 48 adelically. So here's an example of some larger adelic image or a larger adelic index. Right, but this is exactly the kind of things that I'm interested in now, is what kind of interactions. This is a very mild interaction between 2 division fields where the index of where the intersection of the 2 is just quadratic. How bad can those entanglements be? So
I think the index is even larger, because this is the first isogeny class LMFDB, and you have in this class there are 25 isogenies also, which I think are not, you didn't take into account yet.
Oh,
right?
Do you think this is not, it's not surjective here?
Maybe it is, but maybe, you know, in 25, maybe it's not. 25 image is not the inverse image.
I think you might be right, that modulo 25, yeah, for the image to be exactly 48, the image modulo 25 would have to be the inverse image of this modulo 25, and I believe you're right that it might not be. There might be there might be also more restrictions modulo 25. That's correct.
Yeah. This curve has a 25 isogeny also.
Yeah. Great, thank you. Yeah, so I'll look into that, because that very
so
good.
It makes the example even more interesting, I would say.
Yeah. I think the image, you will be right, and the index will be actually quite larger than that. That's right. Okay, so how bad can entanglements be? So this is some work I did with Harris. We started by trying to understand what's the worst case scenario. The worst case scenario is when 2 division fields, the intersection is all of it. Can you have 2 division fields be identical to each other? So that's a terrible entanglement. And these things can happen. For example, you don't have to go too far to see such examples where, in this elliptic curve, for example, the 2 division field equals the 3 division field equals the 6 division field equals this splitting field. In another case, in this elliptic curve, the 2 division field turns out to be equal to the 4 division field and is Q adjoint I. So you don't have all of the 2 torsion defined over Q, but as soon as you try to define the 2 torsion, you actually get for free the 4 torsion. This is what we call, we call this a horizontal entanglement. when there are 2 primes involved, so that the 2 and the 3 division field are entangled, we call this a vertical entanglement, because these are entanglements between the p division field and a p square division field. Okay, so we studied in a paper that is out there already. We study, like, we actually are not able to complete the classification of these things, but we get quite close. So for example, in vertical entanglements, we prove the following, that if you have an entanglement, a vertical entanglement, that the p to the n torsion field equals the p to the n plus 1 torsion field, then p is 2 and n is 1. So basically that then it is that the 2 division field equals the 4 division field, and we can parameterize all the examples of such entanglements. And also we actually, so one consequence of this, if this is going to happen, what happens is that by the Weil pairing, the p to the n plus 1 roots of unity would be in the p to the n division field. And we actually thought that that was crazy, that couldn't happen, that you would have the p to the n plus 1 roots of unity inside the p to the n division field. And what we were able to prove is that, well, if that happens, p equals 2, and then we were like trying to prove that this doesn't happen for p equals 2 either, until we found that it does happen. So it happens for an elliptic curve with complex multiplication, where in this elliptic curve, and I might have sort of approved that it only happens here, but in any case, it does happen that in the 2 to the n division field, the 2 to the n plus 1 roots of unity are always there for all n bigger than 1. Okay, so it actually happens in the entire tower. They get extra roots of unity ahead of time. All right, so that's a weird vertical entanglement. For horizontal entanglements now, what we are able to prove is the following, that if you have a p to the n division field equal to a q to the m division field, and then it turns out that the equality is just between the 2 and the 3rd division fields. Okay, and we can parameterize all such elliptic curves. And then we're not able to prove all the possibilities for an n division field and an m division field being equal. But what we can prove is that if it is abelian, if that entanglement happens to be abelian, then we can say what happens. Then either the 2 division field equals the 4 division field, and they are both equal to q adjoint I forcefully, or the 3rd division field equals the 6th division field, like this. Okay, but in that case, actually, the 2 division field is not the 3rd division field, because if that happens, then it cannot be abelian. Okay, so you can have this, and we have a parameterization of all those examples in the abelian case. All right, so those are some examples of the worst case scenario of entanglements. So what other types of entanglements can happen? That's Harris and Jackson. So Daniels and Morrow have already started this. There's been work by them on their own, and then I'm joining them in an upcoming paper. There's, by the way, a lot of work on this also by Jones and some of his Nathan Jones and some of his collaborators on these type of questions. So what we're trying to do in this paper is classify what kind of abelian entanglements can happen. So what we're interested in is the following case. So suppose that the A division field and the B division field are entangled, and then if you look at their intersection, we're interested in abelian entanglement. So in their intersection, look at the the largest abelian extension within that intersection. And then if that is non-trivial, meaning that, so D here is the GCD of A and B, then certainly the D division field is inside in the intersection, and we know that the roots of unity are there, and that's expected, and that doesn't cause any problem. That's not an entanglement. That is as it's supposed to be. However, if S here is non-trivial, so if this extension here is non-trivial, then we say that there is an abelian entanglement of type S. Okay. Again, no entanglement means that S is trivial. There is nothing else other than the D roots of unity. So that would be an abelian entanglement. And then what we call a Weil entanglement is when that entanglement is actually coming from strictly from the presence of roots of unity in both sides. So what I mean here is that if you have inside the, for example, in the A division field, some B roots of unity or some piece of the B cyclotomic roots of unity are in the A division field, then automatically by the Weil pairing, they're going to be intersecting with the B division field, right? So that if the intersection comes because of, well, this piece that is cyclotomic has to be inside the other part, that we call a Weil entanglement. So in that case, we say that there is a Weil entanglement of type T in there. I'll give you examples of all of these things. So here's a few examples of abelian entanglements that we've already talked about. I've mentioned the Serre entanglement. The Serre entanglement happens with the, it's an entanglement that occurs with the square root of the discriminant. It's either because the two-adic representation is not surjective, or because the square root of the discriminant is contained in the two division field and is contained in some other cyclotomic field. Okay. There is also something that is related to complex multiplication. So this CM entanglement comes from the fact that if you have an elliptic curve with CM by a quadratic imaginary field K, it turns out that for all n bigger than 3, bigger or equal to 3, K is contained in the division field. Okay. So you actually have K both in the n and the m division fields. In my original statement about the adelic image of the CM case, this is sort of like baked in that theorem, because remember that I told you that after a quadratic extension, the image is abelian. That quadratic extension is this extension. So, so that entanglement is sort of like baked into that theorem. But in any case, if you're just looking for entanglements in the CM case, you would find such entanglements. And is what we call a CM entanglement. And then there are Weil entanglements. And again, Weil entanglements is when in the A division field, there are B roots of unity, then those B roots of unity belong to the B tower, and then there's an entanglement between the A and the B. And it's just strictly because of roots of unity in both sides. Some roots of unity belong to the other division field. Then there are other entanglements that do not come from either one of these, which would be in the A division field, there is some abelian field of some sort that also appears for some strange reason in the B division field. And what we actually conjecture is that those out of nowhere entanglements do not happen other than for a finitely set of J invariants. So our running conjecture right now is that these are all the types of abelian entanglements that can happen, and we're working on classifying. We know how to classify these and these. So we're trying to classify all the possible Weil entanglements that occur. So here is an example of a Weil entanglement. So if you have take D to be a square free and T to be a rational number, then you can define the twists. These are the twists of an elliptic curve defined over Q. It turns out that this image modulo 3 is a split Cartan, and it is precisely, the field of definition is precisely Q adjoint the square root of -3 and the square root of D. So it turns out that then for every one of these elliptic curves, the square root of D will be inside some other cyclotomic field, and therefore the third division field and that other cyclotomic field are entangled, and the intersection is exactly Q adjoint the square root of D, and which will result in an entanglement. And that's what we call an entanglement of type 3n, meaning that the 3 and the n division fields are entangled, of type T equals z mod 2, because the entanglement is just a quadratic extension. So this is a type, an infinite family of Weil entanglements. So here is some of our theorems. First, we prove that there are infinitely many times where the 3 division field and some n division field are entangled, that the 5 is entangled with n, that the 7 is entangled with n, and the m and n are entangled for m in these numbers and n any n, well, for some n bigger or equal to 3. So in a case, we can parameterize all these entanglements that can happen. We also have some theorem about the image in the complex multiplication case. We actually show that the adelic image in the normalizer that I wrote before, it turns out to be 2 in the normalizer. This, again, the image being in here already captures what I call the CM entanglement. So the fact that it's always 2 is that there is always an additional entanglement, which is actually a Weil entanglement in addition to that. And third, we've actually extended our search a little bit into abelian varieties, and we prove that there are entanglements in torsion subgroups of abelian varieties as well. I'm running a little bit out of time, I think. So let me just give, to finish off, one last example of something that is not a Serre entanglement, not a CM entanglement, and not a Weil entanglement. So if you look at the twists of this particular elliptic curve, it turns out that the for p equals 3 and 5, because this elliptic curve has a 15 isogeny, it turns out that in both cases, the abelian, it turns out that the abelian intersection of the p division fields is in both cases just the pth root of unity and a square root of d. So the intersection between the third and the 5th division field, it turns out is just a quadratic field, a square root of d. It is not a CM entanglement because this elliptic curve has no CM. It is not a Serre type entanglement because the 2 division field is not even in the picture. And this Q adjoint the square root of D, as long as you assume that D is not -2, -3, or 5, this quadratic entanglement is not inside the cyclotomic extension, so it's not a Weil entanglement either, as we defined it. So this is a sporadic entanglement, if you will, that doesn't come from any of those, but this example is very specific to the fact that there is a 15 isogeny here, and there's only finitely many elliptic curves with a 15 isogeny. So I can't find many examples like this. So we believe that this kind of example is actually just strange. And in general, all the entanglements that are abelian are of the types that I've defined before. So I think I'll stop there. Thank you.